Alrighty, good afternoon, everyone. My name is Sarah Burke. I am the current chair of the Chemical and Process Industries Division. I want to thank you all for coming and joining us today for this webinar that we'll be presenting. If you're not aware, the Chemical and Process Industries Division, our mission is to facilitate the interchange of ideas, tools, practices, and solutions necessary to address real chemical and process industry problems. And so one thing to keep in mind is although we've got chemical in our name, we are very welcoming across many different industries. So our members could be in pharmaceuticals, the chemical, glass, petroleum, medical device, business processes, engineering, all sorts of different types of industries. And so we're glad to have you join us today. We are going to be having Nathaniel Stevens from Waterloo University speaking to us today. Nathaniel was actually the 2018 Shewhell Award winner at our Fall Technical Conference. So the Fall Technical Conference is our annual flagship event that typically takes place in October. Unfortunately, because of the current conditions, this year's conference has unfortunately been postponed to next year. But we are happy to have Nathaniel here. The Shewhell Award is an annual award given to the person who demonstrated excellence of presentation and written materials at our Fall Technical Conference. It's given every year, and it is an award that is given based on feedback from the actual participants. So everybody votes on what they think the best talk was at the conference that year, and so the winner is graded on the oral presentations from the attendees and also on written materials by a panel of independent judges. So Nathaniel won in 2018 for his talk on comparing Kaplan-Meier curves with probability of agreement. So we're happy to have him here today. And I'll kick it off to you, Nathaniel. I will just point out if there are any questions during the webinar, feel free to use the chat box and we'll be monitoring it. And Nathaniel can answer questions as we go and we'll leave time at the end. So without further ado, take it over, Nathaniel. Thank you so much.
Oh, thank you. Thank you both, Sarah and Mickey, for inviting me and for organizing this. I'm definitely happy to be a part of this. And thank all of you as well for attending this webinar and joining me on whatever morning, afternoon it happens to be for you. Hopefully everyone's staying happy and healthy during these COVID-19 times. Let me just pause and make sure my screen has successfully been shared. Maybe Sarah, Mickey, you can tell me if you can see it okay?
Yes, it's good, Nathaniel.
Okay, excellent. All right. So as Sarah mentioned, the talk that I'm giving here today is based on the same talk that I gave in 2018 at the Fall Technical Conference. The work has evolved a little bit since then. At that time, the work I presented was a little bit preliminary. Now we're in sort of final revision stages at a journal, and so I've updated the talk to be as current as possible. So without further ado, let me get into it. And what we're going to do today specifically is talk about comparing Kaplan-Meier curves, which in this context are going to be used to estimate reliability curves. And we're going to compare those using a tool called the probability of agreement. So let me, before getting too far into this, I want to acknowledge that this is joint work with Lulu from the University of South Florida. We've been working together on a number of projects recently, and so this one is a joint collaboration between the two of us. So just to give you a brief outline of where we're headed in the next 50 minutes or so, I'm going to talk a little bit about motivating the problem, that is the comparison of reliability curves. I'm going to spend a little bit of time just introducing what is the probability of agreement, because this is a tool that is quite useful for pairwise comparisons and is applicable more broadly than just the comparison of reliability curves. So I'll give a sort of a foundational explanation of what the probability of agreement is. And then we'll talk about how we can use it to compare reliability curves. And so in particular, we're going to talk about how we're going to estimate the probability of agreement. We're thinking of it in this context as a parameter that needs to be estimated with our data. And obviously there's going to be uncertainty associated with that estimate. So we're also going to talk about how to calculate confidence intervals. And we will illustrate this in the context of an example. And then also, I won't spend a lot of time, but I will briefly discuss some results from a simulation study that we undertook in order to make sure that the properties of this estimate in the confidence interval calculation work the way we hope they do. And then we'll finish with some conclusions, and I'll make sure that there's time at the end for questions. But please do, as I'm going through this, if you have any questions, as Sarah said, type them into the chat, and we'll try to address those as we go through this in real time. Okay, so comparing lifetime distributions is really quite relevant in a lot of different topic areas. Three that immediately come to mind are reliability engineering. So that's going to be our focus today, talking about the comparison of reliability curves, which summarize the lifetime of some manufactured product. But this is also applicable in the context of survival analysis, where maybe you want to compare the survival functions of two different arms of a clinical trial, or maybe two different cohorts in some sort of observational study. We also care a lot about lifetime distributions in the context of customer analytics. So many data scientists who work for companies that care about acquiring and retaining customers, care about the lifetime of a customer, and would like to, if the need arises, compare perhaps different cohorts of customers in terms of their lifetime distributions. Maybe they run an A/B test of some kind and try to determine whether some treatment condition extends the customer lifetime as opposed to a control. So anyway, lots of different application areas where the goal is to compare lifetime distributions and effectively evaluate whether they're similar or different. And as I said, though, the context that we're going to talk about today in terms of notation and nomenclature is going to be the comparison of reliability curves. So there's a lot of ways to do this. In particular, lots of ways of estimating reliability curves. We have a lot of parametric approaches in terms of, say, like Weibull regression models or log normal regression models. But then there's also non-parametric approaches like the Kaplan-Meier estimator, which is this sort of product limit estimator where what we're estimating is this survival function, which for purposes of the talk today, we'll call this the reliability function, which is the probability that a lifetime exceeds some value T, and now T might measure time, it might measure cycles in the context of an accelerated life test, but that's the quantity that we're trying to estimate. Let me just use a laser pointer. So this is what we're estimating here, and we can do that, and we'll do that in the context of today's talk with the Kaplan-Meier estimate. And so this usefully accounts for censoring, in particular right-censored observations, where you may not know when a particular unit fails, you just know that it's lived to some duration that you've observed. So this is the estimates like these are the ones that we want to compare. And so we would like to do that over an entire time frame and by that I mean many different values of T. And if we can, evaluate whether the similarity or difference between the survival curves or the reliability curves depend on time, because it could be the case that the two Kaplan-Meier estimates are very similar early in the time window, but quite different later on. And we would like to account for that if that difference arises. So as I said, the goal then is to compare the two underlying reliability functions, which we'll call S1 and S2. And I would say that the most common way of doing this, the method that is most commonly applied, is with just a standard hypothesis test of the form that I've got on the screen here, where our null hypothesis is that these two reliability functions are identical. And then the alternative that is to be contrasted with that is that there's a difference. And the routine ways of testing this hypothesis are some of the following. The G-row class of tests is probably the most general, the most general version of these things. The Mantel-Haenszel log rank test and the Gihan-Wilcoxon test both arise as special cases of the G-row class of tests. But these are used to test a hypothesis that looks like this. And the way they typically work is they look at all of the different failure times that are observed in the two different groups. And it's a hypothesis test where the test statistic is comparing observed versus expected failures. And that's aggregated over the entire time window. And you would reject the null hypothesis if there was a big disparity between observed and expected numbers of failures if that null hypothesis were assumed to be true. And what we're going to do instead, and I'll talk in a few minutes about why or where there are deficiencies in these hypothesis tests, we're instead going to compare the Kaplan-Meier estimates using the probability of agreement. And we're going to do this in the context, as I said, of an illustrative example. And the one that I'm going to talk about is a toaster snubber example that Wayne Nelson published many years ago. And this example is going to pop up again and again throughout this talk. So it's worth sort of spending a minute here to set the stage and explain this context. So the data set, the original publication talked about an accelerated life test where different snubbers, and I'll explain a snubber in a second, were compared. So in a toaster, you can imagine pushing this little lever all the way down, and then your toasts or your bread descends into the toaster. And then when they're done, this lever pops back up when your bread becomes toast. And the snubber is this mechanism inside this lever that mutes the ejection force. So if the snubber didn't exist, or if it was broken, the spring that shoots this lever back up would have no resistance against it, and your toast would just fly out of the toaster. So the snubber is this mechanism that mutes that the spring, so that the toast kind of gradually come up in a I don't know, straightforward in a way that is not violent. Anyway, so that's the snubber. And the example is an accelerated life test where two different versions of this snubber were manufactured and compared in terms of their lifetimes. So in particular, the data set contains 106 observations, or rather 106 units. Well, yes, a unit is an observation, so what I said first is still true. But so there's 52 old snubber or old toasters made with the old version of the snubber, and then 54 toasters made with the new version of the snubber. And what we have are data that look like this. These are the 52 and 54 observations, where every observation is an event. And if there's a plus beside the number, it's a right-censored event where we don't actually know when the toaster failed or when the snubber failed. All we know that it was sometime after the number that's to the left of the plus sign. Let's look at this in a more useful way with a picture. And so what we have here, I forgot to put a legend on, but the circles that are closed, those represent observed events or observed failures, and the open circles are right-censored observations. So on the horizontal axis, what we sort of consider time here are number of cycles. So a number of times that the toaster lever was depressed and the snubber was exercised. So that's our horizontal axis here. That's what the T in all of our formulas are going to represent. And just by quickly looking at these pictures, comparing the left to the right, you can see, I think, that the snubber lifetimes tend to be a little bit longer in the new manufacturing or the newly manufactured SNUBBERs versus the old version of them. So that's the raw data. We can estimate the reliability curves using the Kaplan-Meier estimates, and that's what this picture here represents. So black, again, just like this last picture on the left, was old. Gold is new. That color scheme carries over here as well. And what we can see here, a few things, that early on in this time window, the solid lines, which are the Kaplan-Meier estimates, they track each other fairly well. There's not an extremely noticeable difference. But as time goes on, or rather as the number of cycles increases, the new toaster or the new SNUBBER design seems to outperform the old one. So that's one comment. Another comment is that these dashed lines, which represent the 95% confidence intervals for the Kaplan-Meier estimate, we can see, not surprisingly, that they get wider and wider over time. And what's happening there is that just as the number of cycles increases, we have fewer and fewer observations lasting that long. And so when we get into that region of little to no data, there's a lot more uncertainty around those estimates. So those are sort of two key takeaways from this picture that we want to account for and remember when we make a formal comparison between these two curves. So just to remind you, they are that the lifetime seem to be longer in the new condition relative to the old, as the number of cycles increases, and then also the uncertainty gets larger as the number of cycles increases. Okay, so that's what we want to compare, are the two reliability curves. We talked briefly about a couple different hypothesis tests that can be used to do this. So what do they say? And if we do the calculation, the Mantel-Haenszel log rank test gives us a p-value of roughly 0.7, and the Gihon-Wilcoxon has a p-value of roughly 0.8. So these are really large p-values. There's barely any evidence at all against the null hypothesis. And so if this were the approach that we take, we'd conclude that we don't have enough evidence to reject that null hypothesis. And therefore, we sort of carry forward with the assumption that the underlying reliabilities are the same. Now, the caveat here, there's three of them in my mind, and these aren't specific to necessarily, or some of them anyway, are not specific to the Mantel-Haenszel and Gihon-Wilcoxon test. Some of these are deficiencies of just hypothesis testing in general. And the first one is that statistical significance is a function of sample size. We all know that if you take your sample size to infinity, any difference you find, you'll conclude that it's statistically significant, regardless of whether that difference is practically meaningful. So that's one deficiency to recognize. The next two are specific to these two tests. This second bullet here is that these results don't allow for time varying conclusions. We basically distill our comparison down to a single number that doesn't depend on time or the number of cycles. And I think that's an oversimplification that could potentially miss, or I guess just miss important information. So these hypothesis tests don't allow for time varying conclusions. And then the third one is that for these hypothesis tests to be valid, it requires that the proportional hazards assumption be a valid assumption, which may or may not be the case. So for example, if the survival curves intersect one another, that's a violation of the proportional hazards assumption. And if that's the situation you find yourself in, then the results that you get with these hypothesis tests are going to be less credible. So these are three sort of deficiencies, and my intention is to overcome them by using the probability of agreement. So that's where we're headed next. So let me just spend a minute talking about what is the probability of agreement in a little bit of generality. So typically when people do two group comparisons, and this doesn't have to be reliability comparisons, it can be comparisons of means, proportions, variances, whatever the case may be. Those sorts of comparisons are often made in the context of a two-sample hypothesis test, or maybe some sort of a regression model, or even something more complicated than a regression model, where there's maybe a term in that model and your hypothesis test centers around whether that coefficient needs to be 0, and whether there's need for two separate models or a single joint model. But the underlying theme is that these hypothesis tests are making a null assumption of equality. And with your data, you're searching for evidence of inequality. And that's not always the best thing to do, or the safest or most reasonable thing to do. You might imagine in many cases when you're manufacturing, say, the same product but by a new method, it's not, there's no sort of engineering or practical reasoning behind why you would expect things to behave in exactly the same way. It might be safer to start from the assumption that the things are going to be different, and what you're looking for in your data is evidence to suggest that they're the same. So it's reversing the role of the null and the alternative in traditional hypothesis testing. And this is the philosophy that underlies equivalence testing, which is grown very widely in popularity in recent years. And the idea with equivalence testing is exactly this, that you start with a null assumption that the two things you want to compare are in fact different, and then you use the data to look for evidence that they might be the same. So equivalence testing is used quite regularly in bioequivalence settings, particularly in pharmaceutical development. But in more recent years, it's beginning to get more widespread adoption in many different areas. And so that's exactly what the probability of agreement is, or I shouldn't say it's exactly, the probability of agreement was designed to answer the same question in the same spirit, but without doing a formal hypothesis test. And this is especially relevant now today amidst the sort of culture of skepticism around p-values and null hypothesis significance testing. And if you've seen in 2016, the ASA released a formal statement on p-values. And then earlier this year in March, the American Statistician had a special issue devoted to this sort of the controversy around p-values and moving to a world beyond quote unquote p less than 0.05. And in all of this recent literature, I think one of the main themes that has arisen is that we should try to complement hypothesis testing with more estimation-driven approaches, and in particular try to account for practical significance, not just statistical significance. And so that's exactly what this probability of agreement is designed to do. It explicitly quantifies whether or not the difference between two groups is practically relevant. Or in other words, we're going to calculate the probability that the two groups are practically equivalent. So in order to do this, we need to have a notion of what does it mean to be practically equivalent. And in the bioequivalence literature, there's a number commonly referred to as the equivalence margin, which is basically, we're going to call that number delta in this talk. So if we think of the range between plus and minus delta, that gives you a region of basically practical equivalence, where any differences within plus and minus delta would be considered practically negligible. So that's sort of our context. And we need to be able to make a decision about what that practical equivalence might look like. So this is the probability of agreement, sort of in generality. And in a series of recent papers, myself and a variety of different colleagues have applied this probability of agreement idea to the comparison of lots of different things. So in particular, where this first started was in my PhD dissertation was around the comparison of measurement systems, where maybe you have a new measurement system and you want to compare it to your existing one, because what you care to determine is whether or not they behave similarly or differently. And so the probability of agreement is useful in that setting. And then since then, I've come to realize that it can be applied in a variety of different scenarios. So we might compare response surfaces, either expected or predicted response surfaces, in the context of sequential experimentation that you often see in response surface methodology. You can use this sort of idea of agreement, and in particular the probability of agreement, to compare follow-up experiments to previous experimental results. And as we'll see today, we can also compare reliability curves in this way too. So that's the probability of agreement. In this setting, where what we want to compare are the Kaplan-Meier curves, we define it in this way. So it's the probability, basically, the difference between the Kaplan-Meier curves are in this region of indifference. There are some folks in the Bayesian paradigm who refer to this region plus negative to positive delta as the region of practical equivalence. The acronym ROPE is sometimes used. But nonetheless, what we're asking is, what is the probability that the difference between our Kaplan-Meier curves lies within this indifference region? And if this value is high, so if the value of theta is a large number, close to 1, then that gives you evidence to suggest that the underlying reliability curves are reasonably similar to one another. But if theta is a small number close to 0, then that's giving you evidence to suggest that, that these underlying reliability curves are probably not so similar. Now, I'll emphasize the fact that this is a function of t, so we're not going to calculate just a single number that is meant to be applicable over the entire time horizon. We calculate this at every single potential value of t you might care about, so that's already beginning to overcome one of the deficiencies of the hypothesis test, and so we'll see here that we're able to draw time varying conclusions. This last bullet point I've already mentioned, but the one thing I want to add to this is to say that while large values of theta give you evidence to suggest there's agreement between the reliability curves, the value of theta beyond which you're comfortable making a conclusion, yes, these two things are in acceptable agreement or they're practically equivalent, that's up to the user. So for somebody, maybe as long as theta is bigger than 0.7, that gives them enough evidence to believe that the reliability curves are practically equivalent. Other people might be more stringent and require that theta is bigger than 0.9. And so it's important just to acknowledge that there's an element of sort of user, what's the word I'm looking for? I don't know, basically it's user driven, that they can tailor the analysis and the decisions to meet their needs. Okay, so let's carry on. One thing to note, given that this probability of agreement is defined explicitly in terms of Kaplan-Meier estimates, which are step functions, this probability of agreement estimate is also going to be a step function. So just if you're imagining what this is going to look like in your mind, the plots of the probability of agreement are going to be step functions. In terms of where we're headed with the talk, we're going to talk about one way of estimating them and 3 different ways of calculating confidence intervals. One that's going to rely on sort of large sample normal theory, and then 2 non-parametric alternatives based on bootstrapping. So how do we estimate the probability of agreement? It turns out that using the asymptotic normality of Kaplan-Meier estimators, that we can distill this probability of agreement estimation to basically a standard normal probability calculation. So as you're probably well aware, the Kaplan-Meier estimator asymptotically follows this normal distribution. So as our sample size gets bigger, the sampling distribution of the Kaplan-Meier estimate should look normal. And this particular variance is what is referred to as the Greenwood formula for variance. And some people like using it, some people don't. The people who don't like it often cite the fact that if you're trying to do confidence intervals for the Kaplan-Meier estimate, intervals based on this variance term can go outside 0 or 1, which is obviously problematic because the Kaplan-Meier estimate is an estimate of a probability which is bounded within 0 and 1. So what some people do instead is to do a transformation of the Kaplan-Meier estimate, like the complementary log-log or the logit transformation. So we could also do that here. We could back up and define our probability of agreement rather than in terms of the Kaplan-Meier estimates, instead in terms of some transformation of them, so that we get sort of nicer behaving confidence intervals. But the reason we don't do that is because it's really hard to define what delta is on those transformed scales. It's hard to come up with a value that has some sort of practical meaning on the, for example, complementary log-log scale. That will back transform into something meaningful on the original scale. So like, for example, if delta is 0.05, it means that a reliability of 0.9 and 0.93 would be considered practically equivalent, but a reliability of 0.9 and 0.97 would not. And it's that sort of intuitive comparison that we really want to hang on to. So it's for that reason that we move ahead using the Greenwood formula for variance, because it allows us to use untransformed Kaplan-Meier estimates. So if the Kaplan-Meier estimate in one group has this normal distribution and we assume the groups are independent, then we have this normality of the difference. Through the next couple slides, we're going to refer to the true difference in reliability curves at a particular time as S sub 0. So that's where this notation is coming from. So in terms of estimating this, we're using the asymptotic normality to say that this probability statement is approximately equivalent to this difference in standard normal CDF probabilities. And we estimate that basically by plugging in the estimated difference in the Kaplan-Meier curves, where in this statement, we have the true difference. So that's how we estimate it. And then we basically just plug in a bunch of different values of t that are of interest to us. And so a systematic way of doing that is to start at 0 and maybe go to the maximum lifetime that you observed in your data, or even beyond if you want to do some extrapolation. But what we're going to do is plot theta hat versus t to sort of understand how the agreement between these reliability curves depends on time. Okay, so that's the estimation piece. We'll next talk about how to calculate, or one method of calculating a confidence interval, and then I'll show you some pictures. We calculate the variance of the estimate of the probability of agreement using the delta method, and it can be shown that the estimated variance looks or is this term. I won't work through the details here though, but we basically exploit that and we calculate this walled type confidence interval, where if your confidence level is 1 minus alpha, we're just doing estimate plus or minus the appropriate standard normal critical value times the standard error of the estimate. So this does have the potential deficiency that the interval could go outside plus 1, or sorry, below 0 and above 1. And the way we handle that for this case is just to truncate that. I notice there's maybe a question. Good question. The data presented was in terms of cycles, how you convert this to time. I'm kind of using the word time and cycles interchangeably here, and kind of by accident. So when I talk about time, what I really mean are cycles, particularly in the example that we're talking about, the SNUBBER example. Okay, I can close this. So the different values of t would be the different increments of cycle numbers, and we'll see that in the plots to come. So here's one plot. So on the left, I have the same Kaplan-Meier plot that I showed you before. And then on the right-hand side, we have the probability of agreement calculated with delta equal to 0.01. So this is a reasonably strict criteria that says that the two reliability curves, or in particular, the two Kaplan-Meier estimates, have to be within plus or minus 0.01 of each other for us to consider that practically equivalent. And so the blue line on the right-hand plot tells us what is the probability of that happening. And then the red dashed lines, that's the point-wise confidence interval. And that's one other point that I want to make. Let me back up here for a second, that these calculators are, the confidence intervals are calculated in a point-wise fashion. We did consider calculating a simultaneous confidence interval with which you would sort of interpret it as wanting to encompass the entire true value curve over the time or cycle horizon. But we found that unless your samples were really, really large, those confidence intervals were just like unusably wide, basically lower bounds of 0 and upper bounds of 1. So we're taking the approach just to calculate point-wise confidence intervals. And so it's important to acknowledge that when we're interpreting this plot. And that gives rise to this sort of bubbling shape that you see here, where we have a lot more certainty around the observed failure times and less certainty in those other regions where there weren't observed failures. So that's the probability of agreement calculated and confidence intervals calculated when delta is equal to 0.01. And this curve is going to change dramatically for different values of delta. And it's important to recognize that. And that being the case, it's important to think carefully about the value of delta that is relevant and applicable to you. And you want to choose that carefully such that your conclusions that you're going to draw are meaningful in your context. So the next picture is identical, except that delta is now 0.05. So we're still comparing the same two Kaplan-Meier curves, but we've become less strict. We've said that this region of practical equivalence is between plus and minus 0.05. And so you can see that the blue curve relative to this previous one has sort of systematically increased. And the nature of our confidence intervals has also changed. In general, they've widened a little bit, and this illustrates that we've decreased our certainty with this larger value of delta. And we can increase that again to 0.1, and what you see again is just this probability of agreement curve increasing, and the confidence intervals sort of adapting accordingly. Okay, and so the general trend that we see here is that the probability of agreement increases, and I've mistakenly put time on this axis, but what this really is are cycles, number of cycles. So as the number of cycles increases, what we're seeing is that the agreement between the Kaplan-Meier curves decreases. And that agrees with what we saw on the left-hand side here. And in particular, though, I think that this probability of agreement curve probably descends more quickly than you might have expected, given what seems to be good agreement through this region here that I'm highlighting with the pointer. But the reality is, in this region, and as cycles increases, we become less certain of these estimates. And so there are possibilities, lots of possibilities within these confidence intervals where these Kaplan-Meier estimates are not within plus or minus delta of each other. And that's reflected in this decreasing trend that we see in the probability of agreement plot. So that's a really valuable insight that the probability agreement has captured, that just because these visually look like they're lying on top of each other doesn't mean that they're necessarily equivalent, practically equivalent, because there's a lot of uncertainty. And that's especially true because these are relatively small data sets. So next, we considered two bootstrapping alternatives to calculating the confidence intervals. So the way we do this is, in the first way, is what we just call the ordinary bootstrap. There's nothing fancy going on here. Our data consists basically of pairs where we have an event time and then a censoring indicator that tells you whether that time corresponded to an observed failure or a right censored observation. And what we do is basically just resample those pairs, those observations with replacement. If we had RJ observations in group J, then we're going to make sure that our bootstrap sample has that same size, RJ, where because of the sampling with replacement, we have potentially some observations repeated and potentially some observations absent entirely. And so we can think of this really as assigning in a random way non-negative integer weights to every observation. And thinking of those random weights as coming from a multinomial distribution. And so just to sort of illustrate that, here's an excerpt of the data from the SNUBBER example for the first group, the old SNUBBER. So these middle columns represent the observed data. And then the weights here, these multinomial weights, they're these integer weights basically representing the number of times a particular observation occurs in the bootstrap sample. So for example, this first observation, it's not going to be included in the bootstrap sample at all, whereas the second observation is going to be included twice. And so we can think of the bootstrapping in this way, and thinking of generating these weights as integer weights from a multinomial distribution is going to be a useful way of thinking about this process when we start talking about the fractional random weight bootstrap. But really nothing different is going on here than an ordinary bootstrap. So what we do is for every bootstrap sample, we're going to calculate the Kaplan-Meier estimates in each group. We're going to repeat this across every one of the bootstrap samples. And if there are B of them, that's going to give us B estimates of the reliability curve in group 1 and B estimates of the survival curve, reliability curve in group 2. And with all of those B pairs, we can calculate the probability of agreement. And so that's going to give us this bootstrap estimate of the sampling distribution of the probability of agreement. So that's what this notation is here. We have B theta stars, and those are our probability of agreement estimates on the B different bootstrap samples. And in terms of a confidence interval, we're just going to apply the ordinary quantile method, where if our confidence level is 1 minus alpha, then we're going to pick off the alpha over 2 and 1 minus alpha over 2 quantiles from this bootstrap distribution, and we're going to use those as the endpoints of our confidence interval. I will point out that we did consider other versions of bootstrap confidence intervals. If you're familiar with the literature, there are some bias corrected versions of this quantile method, and we tried them but found that they really didn't make a difference. So we're just carrying on with the straightforward approach that I've just mentioned. So here's what we find when we do that. And I'm going to go through the same sequence of plots that we did for the previous version, where on the left, we've got the Kaplan-Meier estimates. On the right-hand side, we've got, again, the estimate of the probability of agreement. That's unchanged. That's exactly the same as how we calculated it before. The only difference is in how we're calculating the confidence intervals. And so you can see that there's just visually a drastic difference between what we're observing here with these bootstrap intervals versus the large sample normal theory ones. These ones are a lot less bubbly. They look like they just behave a little bit more smoothly. And as I'll discuss in a couple minutes, it turns out that the coverage is actually better with these bootstrap intervals as opposed to the large sample normal theory ones. So let me just quickly go through different values of the deltas. So as before, we're ranging from 0.01 to 0.05 to 0.1, and we're seeing the exact same change in probability of agreement that we saw before, but we're also seeing how these confidence intervals adapt as delta increases. In particular, we become less certain of our estimate, and that's not surprising. If you have a really strict tolerance region, so a really small value of delta, then you're going to be fairly certain that the Kaplan-Meier curves are not within that small difference. And analogously, if you took delta to be really, really big, then you'd be fairly certain that the Kaplan-Meier curves are contained within plus or minus delta. So at those two extremes, you're going to be a lot more certain about your estimates, and your confidence intervals are going to be more narrow. But in this sort of middle ground, we are less certain, and that's reflected by wider intervals. Okay, so that's the ordinary bootstrap approach. And the main comments I want to make here is to acknowledge why we didn't just stop. And the reason we didn't just stop is because the ordinary bootstrap works reasonably well. In fact, it works quite well as long as your censoring rate is not too high. And the issue that you come against is if your censoring rate's really high, then you don't have very many observed failures in your data set. Most of your observations are censored observations. And given this nature of bootstrapping, where sometimes an observation could be in a bootstrap sample, or maybe it won't be, it's quite likely that if there's very few observed failures, that there's even fewer represented in a bootstrap sample. And that being the case, that can really compromise your estimate of the Kaplan-Meier, or your Kaplan-Meier estimate of the reliability curve. So we wanted to consider what could we do differently that is robust to this situation, which is quite common. Large censoring rates are a common occurrence. And so what we do to overcome this is a fractional random weight version of the bootstrap. And so the only difference with what I'm about to talk about is how the bootstrap sample is collected, or how it's taken. Everything else is exactly the same. So the key difference is, rather than assigning non-negative integer weights, like we just talked about, these sort of multinomial weights that are maybe 0 or and if not, some non-negative integer. And what I didn't mention, but is relevant now, I shouldn't back up so far, is that these multinomial weights, they're going to sum to your original sample size. So in this case, when we're talking about the old SNUBBER, there were 52 toasters in that condition. So these weights would sum to 52. And what that, the reason that's the case is because our bootstrap sample has the same size as the original sample. So what we could do, rather than this sort of integer weighting, is to do a sort of a fractional random weight, where every observation gets some non-negative weight that is a fraction, that's where the name comes from, but still constrained so that they sum to the original sample size. So this is basically trying to avoid the problems that you might encounter with the ordinary bootstrap. So it's basically these fractional random weights that are non-zero, but also sum to the sample size. So let's illustrate that again with this toaster data. The 4 left-hand columns are exactly the same as what we were looking at before. The right-hand column is new though. The right-hand column is one potential bootstrap, fractional random weight bootstrap that you might take, where every single observation you can see now has some weight. So in some sense, we're getting a little bit of information from every single observation. We're not ignoring anybody. There's, in some sense, going to be a piece of every observation in our bootstrap sample. And if we were to add up all of these fractional random weights, they would again add up to the sample size, which in this case is 52. And the way we have drawn them is just following the fractional random weight convention, is to draw them from a uniform Dirichlet distribution, and then we scale them, those random draws, so that we get this summing property where they are constrained to sum to the sample size. So if that's our approach, then the way we calculate the Kaplan-Meier estimate is unchanged. This is sort of your standard, or I shouldn't say standard, an ordinary life table, which shows how you calculate a Kaplan-Meier estimate at a variety of different time points, or in our case, for a variety of different numbers of cycles, where you have number of units at risk of failing at a particular time, and the number of units that failed at a particular time. But rather than the number of failures being an integer, as it normally would be, we're getting these fractional observations because of this fractional random weighting. So if you'd like, when the slides are posted later, you can look through these calculations to make sure that it is doing the intuitive thing. But that's the only difference, honestly. The way we calculate or the way we obtain the bootstrap sample, and therefore calculate the Kaplan-Meier estimates. Everything else is the same. We do this same procedure on every single bootstrap sample in particular, we'll get B of them. For every bootstrap sample, we'll calculate our Kaplan-Meier estimates and a probability of agreement, and calculate a confidence interval based on that bootstrap sampling distribution using the quantile method. So exactly analogous to what we did with the ordinary bootstrap. The only difference is that we did this fractional random weighting rather than the traditional multinomial integer weighting. So to illustrate the impact that has, from left to right, the left are the plots you've already seen. These are the probability of agreement with 95% confidence intervals calculated using ordinary bootstrap. And then on the right-hand side, we have the same thing, but where the intervals are calculated with the fractional random weight bootstrap. And you can see that they're very similar, that there are differences. If you look closely enough, these aren't identical. And if censoring rates are not too high, then this is expected, that the ordinary bootstrap and the fractional random weight should behave fairly similarly. And that happens to be the case here. The censoring rates were roughly 60% in the old condition and roughly 70% in the new condition. So that's why we're seeing fairly similar patterns here. But let's just bump up delta. Delta's 0.05 now. Again, the dark blue line, that's never changing. We've only talked about a single way to estimate the probability of agreement. But you can see that on the right-hand side, the fractional random weight bootstrap intervals are behaving very similarly to the ordinary bootstrap. But now the nice thing is that we're protected against the situation when you have really high censoring rates, like 95% censoring rates or 99% censoring rates. So that's a definite advantage of this approach. So in terms of the SNUBBER example, I just want to draw a couple quick conclusions. We saw that as the number of cycles increased, agreement steadily decreased. And that is not a conclusion that was available with the log rank type hypothesis tests. And we've also found that the timing and the magnitude of this disagreement, in other words, when do they start to decrease and how quickly do they decrease, that depends on delta. And delta is not meant to be some arbitrary thing that is picked to get a result that you want. Delta is something that ideally would be determined a priori and based on the context and tailored to suit your needs. One thing I didn't point out, but if we look back at these plots, you can actually see that for large numbers of cycles, the probability of agreement starts to kind of tick upward a little bit. And that's not surprising because as number of cycles increases or as time goes on, your Kaplan-Meier estimates and your reliability curves are just going to diverge further and further apart to an extent or at a point which you start to become more certain that they are indeed different. Okay. And then the last one is that the ordinary fractional random weight bootstrap gives similar results. And this happened to be the case because the censoring rates were not too high. But we did investigate through simulation what happens if the censoring rates really are high. And that's where we found in those simulations that the fractional random weight bootstrap really does outperform the ordinary one in terms of coverage when you have large censoring rates. So I don't want to go into, because we're short on time, a lot of detail in the simulation study. But what I'll basically say is that we did a simulation study to make sure that everything worked the way we wanted it to, and it turned out that it did. We investigated two things, basically the properties of the estimator in terms of its bias and variability, and then also the coverage properties of the 3 different confidence interval methods. And we considered 6 different scenarios, which differed in terms of the true underlying reliability curves. Sometimes they were very different, sometimes they were very similar. Sometimes if they were different, the divergence happened right away. Sometimes they were similar early on, but diverged later on. So we looked at a whole bunch of different simulated scenarios that differed in terms of those reliability functions and also differed in terms of censoring rates, some from like really low to really high. And on all of them, we basically evaluated bias and variance and coverage. And some just key results that we found were that bias does tend to exist. It does tend to be minimal, though, in terms of how far off from the true value we are. It's generally on the order of at most 0.1, but that decreases as sample size increases. And as I mentioned back here, the sample sizes we considered range from sort of reasonably small, like our SNUBBER example, to reasonably large, like up to 2,000 observations in each group. In particular, the bias behaved in an interesting way where when the true reliability curves were within plus and minus delta, the bias was an underestimation. And when the curves were truly further than plus or minus delta apart, it turned out that we overestimated the probability of agreement. So just some key things to take away and to acknowledge when you're drawing conclusions. In terms of the variability, variability in our uncertainty was maximized at the point in time or the number of cycles when the true reliability curves were exactly delta units apart, or yeah, delta units apart. And that's not surprising. That's the transition moment when the reliability curves are versus are not truly within plus and minus delta. So there's going to be a lot of uncertainty when we're trying to decide, are they really within plus or minus delta? So there is something intuitively pleasing about that finding. In terms of confidence interval coverage, the large sample normal theory overall did a very poor job. It tended to undercover with the confidence level that we cared about in our simulation is 0.95, and we were seeing confidence levels of closer to in the 70s or 80s, so much less than nominal. In general, the bootstrap intervals behaved much more appropriately, with confidence levels being much closer to the nominal level. And in particular, as I said before, the fractional random weight bootstrap approach was especially good when censoring rates were high, as opposed to the ordinary bootstrap, which that's tend to be when it breaks down. So just to summarize here, we'll be done in about 30 seconds. The probability of agreement, as I see it, provides this intuitive and practically useful way of comparing two statistical characteristics. And we've adapted that here and applied it in the context of comparing reliability curves. Some advantages that it has over ordinary hypothesis testing is that we're able to draw time-dependent conclusions. We're not constrained by sample size. As sample size increases, there isn't a foregone conclusion. And nowhere have we needed to make the proportional hazards assumption. So it's sort of robust to the situation when your reliability curves might intersect. And then the other advantages are more practical ones. And it's basically that you can tailor this approach in any way that is appropriate for your circumstance. And there's two parts to this. One is, what is delta? How different do these things need to be before you say that they're no longer practically equivalent? That's up to the user and is context specific. Similarly, how large does the probability of agreement need to be in order for you to make the conclusion that these things are practically equivalent? Again, that's up to the user. These sorts of user specified decisions, I think, protect this approach over some of the or relative to some of the issues that you see with hypothesis testing, with p-hacking and things like that. So very customizable and very practically driven. If you want to try this out yourself, there is a Shiny app available. If you follow this URL, you can upload your data and it'll do the analysis for you. And I'll stop there. Thank you. And I know I'm just at 3 o'clock now. If anyone needs to leave, go for it. But if you have questions, I'll stick around for a few minutes. And again, please type them into the chat.
So one of the questions in the chat box, is it possible to share the presentation? Absolutely. Nathaniel's given us the approval for that. We'll make sure it gets onto our MyASQ page shortly. And just as a note, we've also recorded this presentation, which we'll make available to our CPID members as well.
Does the method, okay, so there is a question here. Does the method work with comparing exponentially based growth curves? I haven't done that, but I don't see why not. The one thing I found over the last couple of years is that this notion of probability of agreement is super general and can easily be customized to different scenarios. So I think that comparing growth curves is one such application area. And I didn't mention it during the talk, but we sort of defined the probability of agreement in terms of estimators and taken a very frequentist approach to this. But myself and colleagues have also taken this the direction of the Bayesian paradigm, where maybe the curves that you're comparing, you want to do so within a Bayesian context, and the probability of agreement nicely generalizes to that situation as well. You're rather than using estimators, though, you're treating the parameters themselves as random variables. But the general thing that seems to be true here is that if there's two things you want to compare, the probability of agreement is a useful way of doing that.
Alrighty, well, if there's no more questions, I want to say a big thank you to Nathaniel for speaking with us today, and also thank you to Mickey for coordinating everything, and also one last thanks to Carly Metcalf, who helped with our advertisement for the webinar. So thank you all for joining us. We'll make sure to get these materials on our My ASQ page so you guys have access, and just want to wish everybody a safe time in these times right now. So thanks all much for joining us today.